Okay, I think you can see the cover page now.
Yes. Yeah.
Okay,
Go ahead.
excellent. Well, first of all, let me just say it's a great honor to speak to this group at CASPA. It's a wonderful history that you have, a great legacy of 30 years. And Navitas is very happy to present our information about GaN technology, GaN fast power ICs to this group. We are a US company. We recently went public on the NASDAQ Stock Exchange last October 19. And so we're very proud and happy to have reached that stage after 7 years of development focused completely on GaN and doing something that no one else had yet done in GaN, which was integration. So bringing drive, control, and protection features on the same chip as the power device. And through doing that, well, bringing higher efficiency and improving the environment through reducing carbon emissions and overall our effort to electrify the world. We are an American company, but we are also a pretty heavily Chinese company. We have, I think, about half of our employees are China-based, and many of our US employees are Chinese-American semiconductor professionals. In China, we're often known as Naowei, Nanomicro, and our mascots, Xiaodan and Xiaojia, are getting to be well known in China as well. So let's talk about energy. The way we use energy now is we pretty much dig it out of the ground. With fossil fuels, or let's just put uranium in the same category. Things that are pulled out of the ground and used directly through some form of combustion, or in the case of nuclear, of course, fission, to generate energy. Not very much energy, maybe less than 20% is renewable energy coming from water, wind, and solar. And our methods of delivering energy from remote sources of fossil fuels, power plants, those kinds of things are rather inefficient. The transmission and distribution system creates a lot of losses. So a very small percentage of energy is actually used as electricity in its end form. What we really want to do over the next 30 years is go to reverse that and go to 80% renewables. Directly use that energy at the point of generation, so we don't have to have low efficiency transmission and distribution. Alternatively, have high efficiency transmission, such as high voltage DC, several hundreds of kilovolts of DC to pass electricity from high renewable availability regions to low renewable availability regions. And then everything can run off electricity. Well, not everything. There will still be need for a very high energy density fuel in some fields like aviation and space launches and things like that. But let's try to move almost everything we can to clean, sustainable electricity. This slide is describing the what we call the second revolution in power, and that's our perspective. And we look back here about 40 years, well, let's say 50 years. Am I getting the math right? Looks like a 50-year span. So it's now up to about 45 years. I've been working 43 of those. Back in those days when I started my career, the dominant technology for power conversion in electronics were silicon bipolar transistors, BJTs. Around the time I started working, after I graduated from university, a new device, actually introduced by International Rectifier and the team that I was working in, a couple of months after I got there, power MOSFET technology was introduced commercially. And about the same time, controllers were introduced. So ICs that could control the power conversion process. So that sort of changed the world from linear power, which really was only, 30% efficient, 40% efficient, to switching power, which quickly was able to demonstrate efficiencies of 70 to 80%. And that pretty much took over the power supply industry over the following 10 years. And energy losses were cut in half, and the price of delivering electrical power was dropped by a factor of 3. So then, as we see it 30 years later, we're still doing very similar things. We're switching in the range of 50 to 100 kilohertz largely, which we started to do back in 1987. And the efficiencies have gotten a little better as the devices have gotten better and better. So, and our topologies have improved, and we gained about 10%. But we believe that with GaN, and particularly with GaN power ICs, we can now move that efficiency from that 90% mark up to, across many applications, up to 95 to 98 or even higher. Again, cutting losses by a factor of 3 and reducing the cost by a factor of 3. And so it takes many efforts. It takes not only the new GaN devices, but also improved magnetics, improved controllers, improved topologies to do this. So what is enabling this? So gallium nitride, it's a wonderful wide bandgap compound semiconductor. Combine these two elements together and you get a material that can withstand extremely high electric fields, 10 times higher than silicon. It can also have a mobility that's twice as good as silicon due to the heteroepitaxy layer of AlGaN, GaN combined to form a two-dimensional electron gas on the planar surface of the device. That conductive layer of electrons can be managed and controlled with enhancement mode P-GaN gate like we use in our device. And those enhancement mode devices can switch 20 times faster. They have 20 times lower input charge or input current requirements than the corresponding silicon devices. And because of that, and because of the extremely small devices that can be fabricated due to the high electric field capability, 650 volt devices can be made, which will reduce losses by a factor of 3, deliver 3 times higher power density, and can increase the rate of charge on our mobile devices. This is where we focused for our initial efforts by 3 times or more. And we'll talk about some of those examples. And of course, everybody worries about cost, and we'll talk talk about how GaN will actually lower system cost and eventually become, in just a few short years, a lower cost alternative than silicon for the same semiconductor performance. So we have spent the last 7 years building up and developing a proprietary process design kit, working with our partner TSMC. We are building our products on 6-inch wafers fabricated in Hsinchu in Taiwan. I worked with them even before starting this company and continued to work and co-develop that process. And this, though, is Navitas proprietary IC capability, which is based on the TSMC power device. We have many patents on the way to integrate control, protection, and drive features on GaN chips and in other aspects of GaN devices. We are introducing a new generation of products now about every year. We're on our 3rd generation in production and volume now, and our 4th generation is sampling. With these generational improvements and with volume and the learning that comes associated with that, as well as the combination of functions that we can bring more of the value into the GaN product, we are expecting the system to come down and cross over the cost of a silicon-based system in a year or two. How does that happen? Well, it's not only that the device is very small. GaN transistors at 650 volts are 3 or 4 or 5 times smaller than the best silicon devices out there that handle the same currents, have the same RDS on rating. But you don't stop there because GaN, with its incredibly high switching speed, you can easily drive from 100 kilohertz range up to a 1 megahertz range with GaN power ICs. And in the process of doing that, you can drive up the efficiency from the high 80s to the mid 90s. So a new capability, which we recently have introduced in our 3rd generation of products, is what we call GAN Sense. So all of our GaN fast power ICs we refer to as GaN fast because they switch so fast and the systems can operate so fast. We can charge fast. We do many things fast. With GaN Sense, we can bring in additional features. And these are some of the features identified here, such as standby mode. We've raised the rating of our devices that are basically rated at 650 volts continuous, but we allow an 800 volt transient, which is very useful for chargers that face line surges. We have 2 kV human body model ESD capability, which a basic unprotected discrete GaN transistor does not have. And we integrate other protection features, over temperature protection, over current protection, and we sense the current. And sensing the current is actually a big deal in chargers because right now a lot of power loss is wasted, believe it or not, just with a sense resistor. And we've eliminated that loss. So this describes that, lossless current sensing. It's actually a lot of power. It's very interesting that we spend a lot of time in power semiconductors trying to lower the conduction losses of our transistor. And generation after generation, for the 40 years that I've been working, we've been trying to lower the conduction losses, drive down the RDS on in MOSFETs and other types of FETs. And we've made a lot of progress. But then in common systems, almost always in chargers, a sense resistor is applied. And the value of that sense resistor is very similar to the transistor that it is sensing. So the same amount of conduction losses are lost in the resistor as are lost in the transistor. It's very inefficient. So by putting a current sense function inside our GaN fast power IC, the GaN Sense function, we can deliver that current signal to the controller that needs it to provide the functionality, but we eliminate the loss in the resistor completely. And that resistor also creates hot spots around the device. It heats up everything around it. So it's great to keep cool. It's great to save space. It's great to save power. So we can also use that current sensing capability to provide protection. And we can provide the protection extremely quickly. If you use the signal that goes back to the controller to identify an overcurrent condition, respond to it, decide that it's real, and then send a signal back to the GaN power device, it can take 300 nanoseconds. It can take, in the best case, maybe around 200 nanoseconds or a little less. We can detect it right on the chip and take immediate action and protect the device in less than 30 nanoseconds. So it eliminates extra stress on the device. It's a very effective way to protect the transistor from an out of control condition. So this slide describes a little bit about how we get the reliability that we get on our devices. So to make the device easy to use, but through integration, instead of having to have a high current gate driver drive the device, and come up with a special voltage that GaN transistors need to be driven effectively. We integrate the regulator to deliver that voltage, and we integrate the driver so that a simple digital signal can be put into the device, and the driver handles the current requirements from a regulated voltage. That gives you a very clean signal. It also means that the drive signal has no inductance between the driver and the device it's driving. So no inductance means no overshoots, means no susceptibility to noise. It means a very clean, nicely operating circuit. If you look down here below the circuit and you consider a discrete GaN transistor, you can very easily get oscillations, which can be even destructive, but at the very least, inefficient to see a device switching on and off in an uncontrolled fashion. But when you integrate the gate drive, you can drive to high currents, greater than 30 amps. Now, some of our devices are operating at well over 60, 80 amps with clean switching all the way up to that current and no trace of oscillation or overshoot. I already talked about the extra margin that we offer with the 800 volt transient rating. And what we're really proud of is that not a single device that we've shipped in over 35 million GaN fast power ICs has come back from the field in a product as a defective GaN power IC. We now have estimated over 116 billion device hours in the field, which means a fit rate of less than 1. We're very proud of that, and believe that it was essential to demonstrate that kind of performance in order to get the industry to adopt this new technology. And they did, adopt it they did. You can see so many brands, tier 1 OEMs and major aftermarket brands, Lenovo and Dell in the laptop field, Oppo and Xiaomi, even companies like NVIDIA for game players, LG Electronics for their chargers, major brands like Aukey and Anker and Asus have adopted our technology, and using that, they've been able to offer leading edge chargers. We have over 160 in mass production and about as many in development. This was our first market, and so far we're having a great success. Especially many customers in China have adopted our technology, and a large portion of our revenues are generated in China. So we have more to do. The chargers are getting faster and faster, more and more powerful. And that really drives in our favor, because as they get more powerful, it becomes more and more important to fit a certain power into a small case size. You can see this Xiaomi device in the middle top 120 watt device, which is able to charge incredibly fast. And we've been awarded multiple innovation recognitions for these devices. We're now offering devices with even enhanced ratings up to 700 volts continuous. And here's an example of a new product from Xiaomi using Navitas GaN GAN Sense technology. Well, you can charge a 4.5 amp hour battery in 17 minutes from 0 to 100%. So that's amazing, incredible, really, when you think about where we were just a few short years ago, waiting hours to get our devices charged. Now you can do it so fast. It's so convenient, and we love it. So we don't want to stop there. I've already mentioned that TVs, game stations, all-in-one computers, all of these can benefit from the advantages of gallium nitride. Solar can also benefit from the advantages of gallium nitride. whether it's microinverters, such as this testimonial from the company Enphase about GaN, offering great advantages to them, or solar inverters for residential use, home energy storage devices, wall chargers, wall storage devices, and of course, electric vehicle chargers. All these things can benefit from the use of GaN. Data centers can benefit tremendously and save huge amounts of electrical costs by adoption of GaN. We believe that GaN could reduce the cost of electricity by up to 10% in the total delivery of electricity to the core processor. And of course, we all know that electric vehicles are a huge new market for power semiconductors, and we see the transformation happening. The OEMs are adopting new onboard chargers that can charge up to 3 times faster. We're working on chargers that are over 20 kilowatts that are very, very capable of delivering that energy so fast. And of course, when you apply wide bandgap technology like GaN to the traction application, you can save tremendous amount of energy in the traction as well. With that, you can increase the range of the vehicle, or you can lower the battery cost of the vehicle, and you can reduce the charging time. So these are the 3 things that are holding back electric vehicle adoption: range anxiety, time to charge, and cost of the battery. All can be influenced by GaN technology. So these are all those examples. We're looking to bring new products and new technologies into that space, and in order to do so, we've opened design centers focused on, at the system level, on designing power supplies for data centers, designing chargers and DC to DC converters for EVs. The first is in Hangzhou, the second is in Shanghai, and we've started shipping our first higher power devices into these kinds of applications. And we don't want to forget that in everything that we do, we believe it's really important to protect the environment. That's been a major motivation from the very beginning. In fact, in my career, almost the entire 40+ years I've been working, trying to conserve and save energy, address and reduce fossil fuel consumption, minimize the emission of CO2 in the environment. Every GaNFest power IC that we ship, we believe today, if we replace silicon solution with GaN, we save 4 kilograms of CO2. That's pretty good when it adds up to 35 million units. It will be much better when it reaches billions of units. And with the high power devices, that number will go even higher. And also with our generational improvements in both the device and the system. So through doing that, not only can we benefit the chargers and adapters, but we believe we can help accelerate, and I say help, be one of the factors to move the market from internal combustion engines to electric vehicles, and down the road, accelerate that adoption by as much as 3 years. And of course, that adoption being accelerated would reduce the emissions dramatically caused by cars. So as you probably all know, there's about a 30 gigaton per year problem that we're trying to address, the world is trying to address for climate change. We believe that GaN can address a major portion of that requirement. So with that, I want to thank you for your attention and conclude my talk. And I want to wish you a very happy Year of the Tiger. And you can see Xiao Dan and Xiao Jia there. We also call them Gali and Nitro, some of our favorite characters that we've introduced and have become very popular, especially in China. Thank you.
Thank you very much again. That's really cute. Yeah, we love that. Yeah. Okay. Yeah. They're really beautiful. Okay, thank you very much again, Dan, for your wonderful presentation. So we actually got a lot of questions in our chat box about your presentation. So I'm going to pick some of them for us to address in the Q&A session. So I can see there's a question about the application, like how would there being efforts in gallium nitride based on application in the Internet of Things like IoT arena. So about applications.
I'm sorry, which arena?
Let me
What's
just
that?
repeat it. Yeah, repeat again. So yeah, I guess I was too excited about the presentation. So the question is about gallium nitride based on applications in the IoT arena. So I believe the audience want to get an idea about the gallium nitride used in the Internet of Things, IoT applications.
Oh, I'm sorry. Yes. Okay. IoT. Well, so yes, devices, you know, that mount on the wall, home thermostats, or devices, voice response devices, you name it. Chargers are embedded, you know, power is embedded in many of these things. Of course, if they're plugged into the wall, if they're freestanding and don't require you know, external sources of energy, if they're harvesting the power they need from the environment, probably wouldn't play a role. But anything that requires power, whether it's you know, from you know, 20 watts, 30 watts, 50, 100 watts, all these devices can be run much more efficiently using GaN.
All right, yeah, thank you, Dan. There's another question about the voltage range for gallium nitride device. So will 650 volt always be the sweet spot for GaN? Or do you expect GaN to replace 100 to 100 volt applications? That was one of the questions.
We definitely feel that GaN has a strong future in 100 volt applications, or let's just say applications from 40 volts on up to 600 or even higher ratings. We see that silicon carbide is also an excellent wide bandgap technology, and will gradually replace silicon devices over 1,000 volts. And of course, we also see some silicon carbide devices coming in around the 650 volt range and offering high power solutions as well. So there will be several technology alternatives, but yes, GaN will extend down to below 100 volts rating devices as the technology continues to mature and the capacity increases.
Yes, thank you, Dan. Another question about actually about the between the kind of comparison between silicon carbide and the gallium nitride. For instance, like a cost comparison between the two devices. I know this question is a little bit broad. I don't know if there's a way to do the comparison, like a same voltage range or same power range.
Yeah. So I mean, I guess the you know, the key difference is you can make silicon carbide chips and GaN chips with about the same, very similar in size at the 650 volt range, but the difference is in the cost of the wafer. So both have an epi layer. Cost of that is similar. Right now, the main thing about silicon carbide is that you know, a 6-inch silicon carbide wafer costs a lot. I can't tell you an exact cost, but it's definitely about 20 times more expensive than a silicon substrate. So there's that's the major cost difficulty silicon carbide has to overcome. But then the other aspect is that being a vertical device and being a very specialized process, it doesn't lend itself to integration very well. So we can offer these integrated drive protection and control features in GaN and bring a lot of value by doing that. The other thing is that GaN offers a much lower capacitance, much higher frequency capability. So as the power supplies go up in frequency, GaN gets a stronger and stronger value proposition at the 600 volt range compared to silicon carbide.
Thank you. Two more questions. So some audience asking for say GaN is mainly adopted in China market, it looks like. So how about in US or Korea or Japan market? Is there a customer very interested in the GaN fast charging there? Like actually, I just bought my a Anchor charger from Costco. It was very impressive. Like really like the 5-watt size with the 20-watt. We were really happy to buy that. Yeah. So, but we do see that actually all made in China. So I think this audience is asking about the market in in other areas than China.
Yes. Well, so people are benefiting all over the world from GaN in charger technologies. Apple, for instance, introduced a 140-watt charger, and it has GaN inside. So it's not only, and of course, Dell is a U.S. company selling products